Last lecture we have seen that if we have a matrix equation, say 3 by 3 multiplied by x, y, and z vector is equal to b1, b2, b3, yet another vector. This is 3 by 1 and hence this is 3 by 1. We said the meaning of this is this particular matrix A into capital X is equal to B. We are always solving equation AX is equal to B, where capital A is a matrix which we said is a function. A is function from Rn to Rm. If A is m by n matrix. That is what we accepted, and we further understood what do we mean by that function. Suppose domain, in domain we have 1 0 0 0 1 0 0 0 1. This is the matrix in domain which gets transformed under the function f, or we will call that function now transformation. Under the transformation T, first vector, which is our I, we will call it as E1, E2 and E3, because ijk, it is okay with 3-dimensional system, but if we are going to discuss n-dimensional system, ijk will not be sufficient, and therefore we need to have better notation. So E1, E2, E3 is a better notation. E4, E5, E6, En, like that. And what you have here is A11, A21, A31, A12, A13, A22, A23, A32, A33. This is the images. I mean, this is what is the transformation. E1 column vector, which is I for us, the base vector, becomes E1 dash after transformation. E2 becomes E2 dash after transformation, and E3 becomes E3 dash after transformation. So that is what is the definition, the rule by which the transformation takes place. That is what is this matrix all about. All the entries of this matrix will describe what kind of transformation is taking place. And once that is defined, you can check which vector in a domain, which vector in domain x, y, z, which vector in domain gets transformed under T to required vector b1, b2, b3. Okay, that is what we have understood by taking several examples last lecture. And this is the fundamental thing. I mean, if we are in trouble as far as understanding what matrix is, we have to look at it in this point of view, that matrix is a function, matrix is a transformation, and it behaves like this. So you should have that picture in front of you, and independent. Now this notation is such that you need not have to keep drawing geometry for this notation. It is okay if you write matrix, you understand what is happening there geometrically. So as to understand it for the first time, we drew some pictures last lecture. Okay. Now things are not going to be as simple as this, because when we solved ax is equal to b, things were not that easy. We had to have three cases. Case 1, answer was b by a. Case 2, answer was empty set. Case 3, answer was r. So in the similar lines, we will have different sets of solutions of this matrix equation. And if all is well, you may end up getting unique solution like this. But if all is not well, then you may end up getting an empty set as your solution set, or you may get the entire Rn as your solution set, or you may get subset of Rn, but it is not a specific or a particular solution set. So many different possibilities are there, and therefore we need to understand what exactly we are doing and what kind of possibility exists there. And if we know the nature of the solution set, we need to devise a method by which we find out that solution. However, here the word transformation which I have used here, let me just explain you what do we mean by transformation. And in this case, in this theory of matrices, it is linear transformation. Okay, so linear transformation means what? Let me try to explain first, because that we using it while developing the theory, so we need to understand that. Now say for two vectors, if you operate transformation on u of x plus v of y, u of x plus v of y, where u and v are okay, what notation should I create? Let me create the one which is standard. U and v, ux, okay, ux plus vy, where u and v are real numbers, and x comma y belong to your real variables. What we say otherwise, they belong to your domain Rn. Okay, so if you are operating, understand this statement, u of x plus v of y, that means linear combination of x and y, proportions are u and v. U and v are constants, the real numbers. The transformation operated on a linear combination is equal to linear combination of transformations. Okay, this is important. You operate the transformation on linear combination, it is exactly equal to operating linear combination on transformations. Let me explain you what we are trying to say. This is linear transformation overall. I mean, this is what is linear transformation, and right now I have taken only two variables x and y, but it can be written for n variables. Okay, meaning we said we have two-dimensional domain I, j, those are your unit vectors. Okay, and you have two-dimensional codomain, and you have image of say I looking like this, and image of j is suppose looking like this. Okay, then you are trying to search some vector here, search some vector here. So if you look at the picture in codomain, okay, this is our uh, this is our this is our vector x. Let me call this red vector as x, let me call this blue vector as y. Then this red vector we will call as transformation of x. That is what is defined in that matrix. What happens to x under t? It becomes t of x. What happens to y under t? It becomes t of y. Okay, and now you want to get this vector, which is, this is our vector b that you want to get. So simple procedure, complete your parallelogram and you decide what, how much of red and how much of blue you require. So you end up getting u times, so vector b is equal to u times t of x plus v times t of y. Okay, that is what is your vector b. If you look at the picture in codomain, that is what is our RHS. And what we are trying to say is these guys u and v, what you will get here are the proportions that you are supposed to take of x and y and then operate transform them. This is t. So I think x is to be stretched maybe 2 times and y is taken 3-4 times. So this vector is LHS. What is this vector? This vector is u times x plus v times y. That is our this vector, green vector in domain. Its image under t, that is why t of ux plus vy is equal to this. So this is what this equation is all about, and it is called linear transformation, and that is what is the simplest transformation that we can imagine. You may want to study quadratic transformation, cubic transformation later on in advanced studies, but linear transformation is the most efficient and convenient for calculations, and therefore theory of matrices, theory of determinants is also called linear algebra. It is the algebra of linear transformation. That is what is going to happen every time, and therefore it is very obvious and easy to prove that zero vector in domain will transform to zero vector in codomain. We can always put some special values of u and v and we can prove that t of 0 plus 0 is equal to t of 0. So 0 is t of 0. It doesn't change. This is a special case, and I have written it for 2, but it can be extended for n. This is what is a linear transformation, which we will keep on doing. So if we write matrix equation, this is the story which is running behind the screen as far as that problem or that matrix equation is concerned. So every time if we are confused with the matrix equation, we go back to this fundamental and understand what exactly is happening. I pause the video. Now let me take the system of equations which we have already used in last lecture. I think it is x plus y plus z 2x plus y minus z and x minus 2y plus 3z is equal to 2. Okay, now this is system of simultaneous equations that we wish to figure out whether it has got unique solution, it has got more than one solution, or there is no solution, something like that. So corresponding matrix equation we will write immediately. 1 2 1 1 1 minus 2 1 minus 1, 3 x, y, z is equal to 6, 7. Okay. Now this is, let me call this as system of simultaneous equation 1. Now without getting into the details, just using our common sense, if I write S2 as 2x plus y minus z is equal to 7, x plus y plus z is equal to 6, x minus 2y plus 3z is equal to, its matrix equation will be 2 1 minus 1 1 1 1 x minus, sorry, 1 minus 2 3. Will there be any change here? X y z, the vector will continue to remain same, and only change which will happen here is 7 6 2. So if we wish to compare S1 and S2, what we can conclude? For all practical purposes, these two systems are exactly same. S1 is equal to S2. I mean, we will not say S1 is equal to S2. We will say S1 is equivalent to S2. What do we mean by that? That means whatever is the solution set of S1, whatever are the values of x comma y comma z or the triple which will satisfy S1 will also satisfy S2. And if we happen to have a solution set of S2 with us, we can ensure that whatever is the solution set of S2 will be solution set of S1. Because that is what is our common sense. I mean, you don't mind writing these equations in different order. Still the solution set will continue to remain same. So S1 is equivalent to S2. We should write the definition of equivalent. Equivalent system of solutions. Two systems are equivalent if and only if every solution of one satisfies is a solution of two, and every solution of two means system 2 is solution of system 1. Then in such case we will say that systems of solutions are equivalent. They are equivalent. I mean, you can solve S1 or you can solve S2. It is okay. You will get the same solution set. Maybe we will try and figure out which are some more additional conditions on which we can say, okay, let me write down S3 now. When I can see S1 also, and let me write down S3. Let me write down S3. S3 is 2x plus 2y plus 2z is equal to 12. 2x plus y minus z is equal to 7. And x minus 2y plus 3z is equal to 2. Is S1 and S3 equivalent? Yes, because constant multiple of equation number 2 won't change the solution set. Is S1 equal to S3? No, they are different systems. They are different systems. They are different algebraic expressions, different algebraic equations. Systems. But are they equivalent? Yes. S1 and S3 are equivalent because solution set of S1 is a solution set of S2, S3, and solution set of S3 is also solution set of S1. Okay. Moreover, now let me do one more modification and let us see whether it is also acceptable. S4, uh, now I have multiplied equation 1 by 2 and let me add it to 3, add it to 2. So x plus y plus z is equal to 6. I keep my first equation as it is. I write my second equation as 4x plus 3y plus z is equal to 7 and 19 x minus 2y plus 3z is equal to 2. Now we really do not know whether it will give us the same set of solution or not. Is S1 and S4 equivalent? Think about it and you need to give me reason why should they be equivalent. If at all they are, and if they are not, why should not they be? Yes, S1 and S4 are also equivalent because if we get the solution set of S4, it will of course satisfy solution set of, it will of course satisfy S1 and solution set of S1 will satisfy S4. So it follows the definition and hence these systems are equivalent. So now this is a numerical example which I am giving and trying to tell you we mean by equivalent system. But in terms of notation, what are we trying to do here from S1 to S2? What we are doing? R2 becomes R1. Row number 2 becomes row number 1. That is the transformation that we are doing. We are changing row 2 to row 1 and maybe you can write and row 1 to row 2. This is the transformation that we are doing right now here and it is acceptable. So flipping rows is okay. Now whatever is applicable for rows is applicable for columns. So maybe I will give because we will concentrate on the row transformations more than that of column because it is visually easy to understand. However, I can write this particular S1 itself. Look at this. I can write S1 system as y plus x plus z is equal to 6, y plus 2x minus z is equal to 7, minus 2y plus x plus z is equal to 2. Its corresponding matrix equation will be 1, 1 minus 2, 1, 2, 1, 1 minus 1, 3. Only thing what will happen here is now yxz, okay, is equal to 6, 7, 2. This is what is going to be ax is equal to b for this. So you are just flipping to columns. Column 2 becomes column 1, column 1 becomes column 2 and the system continues to remain same. X will be x and y will be y. So corresponding values of x, y, z, that means solution set will continue to remain same. So column, so whatever is for row is applicable for column transformation. However, we are not going to deal much in column transformations. We will concentrate on row transformation. So how do you get S3? S1 to S3. You got S1 to S3 by R1 is R1 is 2 times R1. The new R1 is 2 times the old R1. That is what we do here. That is the transformation what we are doing. R1 becomes 2 times original R1. And what are you doing as far as S1 to S4 is concerned? S1 to S4, what you are doing is you are keeping R1 same, R2 is R2 plus 2 times R1. That is your new R2. Multiply by constant to first row and add to second. Now simultaneously you cannot change all the rows, then it is not going to be equivalent system. You multiply the first by something, add it to second, you multiply third by something and add it to first, and so on. So if you are changing all the 3 rows, then it might not remain equivalent system. You need to do one operation at a time, otherwise you may get confused and you may get wrong answers. So what is this transformation? R2 becomes R2 plus 2 times R1. So these are the 3 linear transformations. These are the 3 row transformations that we are going to use for eventually finding out the solution set. Finding out the solution set. So now I would demonstrate. So far we have been just discussing what do we mean by simultaneous system of simultaneous equations and what is corresponding matrix equation. Now it is time to discuss how do we really get the solution set, and maybe we take the same example and start processing. 56, 46, 45. So 1, 1, 1, 2, 1 minus 1, 1 minus 2, 3. Now these are the 9 important numbers, and while doing calculations you need not have to worry about x, y, z. We know that they are available. What we need to worry about is the RHS 6, 7, 2. So we will consider this matrix. This is augmented matrix. You are writing just the numbers which are important to you. Everything else is not important. So this is first row, this is second row, this is third row. We just take the numbers. We know this is A and this is B. A augmented B. That is what we have written right now. A augmented B. Okay. The algorithm for finding out the solutions is as follows. Make A1, 1, 1. Okay. Now fortunately in the system that we have got, position A11 is already 1. But suppose if I had started with S2, where 2, 1 minus 1 was in the first place, then what would be the first operation? Interchange the rows so that A11 becomes 1. This is step number 1, which we have already got. Now make step number 2, make A21 equal to 0. Okay, so if I want A21 0, this I want it to be 0. So I don't want to change my first row. 1, 1, 1, 6. That is the first row. You want second row, first number 0. So what is the transformation that you are doing? R2 is R2 minus 2R1. Okay, you are multiplying the first row by 2 and subtracting it from second row. So that is why this becomes 0. If you do it for second entry, it will become minus 1. If you do it for third entry, multiply first row by 2 and subtract it from this, so minus 3. 12 is subtracted from 7, so minus. Now these entries are extremely important, otherwise answers are going to go wrong. And one transformation at a time, therefore, because we are doing it for the first time, after you become expert, you can take couple of steps at a time. So this is from here to here. Okay. Now, is the solution set of this system same as this? Yes. Are they equivalent? Yes. Step number 3. Make A31 equal to 0. That is this position. And we can do it by writing first two rows as it is. 1, 1, 1, 6, 0 minus 1 minus 3 minus 5. We want to make this 0. So third row R3 becomes R3 minus R1. That gives you this 0. Correct? So R3 minus R1 is minus 3, 2, minus 4. See, you have to keep watching me because I am going to make mistakes. This is the third step. Let me write down fourth step here. Step number 4. Make A221. A221. That means this position you want to make 1 here, this position. So obviously you are supposed to multiply it by minus 1. Correct? So we get matrix 1, 1, 1, 6, 0, 1, 3, 5, 0, minus 3, 2, minus 4, augmented matrix. What is that we have done? Which transformation? R2 is minus 1 times R2. So we have achieved this. These are called pivots. A11 pivot, A22 pivot. I think pivot only. Okay. So we have achieved this. Now the fifth step is make A32 equal to 0. How do you make A32 0? Now, if you use R1 and R3, you will disturb A31. We don't want to disturb A31 now. It has to be 0. It should continue to be 0. Therefore, what we will do is R3 becomes R3 3 times R2. That will give you A320. 1, 1, 1, 6, 0, 1, 3, 5, 0, 0. That means 3 times this. In 3 now to be added to 11. Aspirant 15 is to be added with minus 4. This is 11. Augmented. This is what you have got now. And then sixth step is make third pivot A33 equal to 1. We want this one and it is easy. Just divide R3. R3 becomes R3 by 11. That gives you 1, 1, 1, 6, 0, 1, 3, 5, 0, 0, 1, 1. Right? So this is your upper triangular matrix. Why we were doing, if you look at A, it is upper triangular. Okay. Now suppose we stop at this point and we say that, okay, we were to find out the solution set of the system of equations in the first place, and we are maintaining the equivalence. Therefore, this matrix, solution set of this matrix is same as that of 1. And now you quickly get into the simultaneous equations, which is x plus y plus z is equal to 6, y plus 3z is equal to 5 and z is equal to 1. This is the system of equations. Now we are left with, out of which we have already got z is equal to 1. If we put z is equal to 1 in second equation, we get y is equal to 2. And if we get put z is equal to 1, y is equal to 2 in the first equation, we get x is equal to. So you can stop at upper triangular and write down system of equations and finish the problem. Or if you really want to get the complete algorithm in place, step number 7 is make A230. Okay, so from here A230, if I want to make this fellow 0, then I should subtract R2 is equal to R2 minus 3 times R3. We will use the last one because we don't want to disturb these two entries, and therefore what do you get here is 1116,010. Now you multiplied the last row by 3, that becomes 3, and you end up getting 5 minus 3 equal to 2. Last row continues to remain like that, 1, 1. Dotted line augmented. Okay, so now you can see that y is equal to 2 we have already achieved. Now next step, 8th step is to make A130. Okay, how do we make A130? R1 is equal to R1 minus R3. 1, 1, 0, 5, 0, 1, 0, 2, 0, 0, 1, 1. Okay. And 9th step is to make A1, 2 equal to 0, and we can make A1 to 0 by just subtracting R1 is equal to R1 minus R2. R1 minus from here. Okay, and therefore you get the system as 1, 0, 0, 3, 0, 1, 0, 2, 0, 0, 1, 1. Now that is the simplest system that you can have, where you have all the 3 pivots and everything else is 0. This is identity matrix I. 3, because 3 by 3. And if you try to write down the solution set or system of equations here, it is x is equal to 3, y is equal to 2, z is equal to 1 is the system of simultaneous equation you have achieved at 9th stage, which is supposed to be the solution set of given system of simultaneous equation. So the procedure is like this. I have demonstrated it for 3 by 3. Maybe you write down properly, understand it. I will give you 3 by 3 new determinant matrix, and you should get the solution set. Now we can always program this algorithm and get the matrices solved. This is the fundamental method of solving a matrix equation. Okay, so if you have understood this procedure, so as to practice and have control on this procedure, I give you 5 by 5 matrix. x1 plus twice x2 plus x3 minus x4 plus x5 is equal to 0, minus 2x1 plus x2 minus x3 minus x4 plus 2x5 is equal to minus 3. After I write 5 equations, I know the solution. Therefore, I will cross check all 5. And after that, you can start. If there is a error, then you will get very bad numbers and you will start shouting at me later on. Therefore, I will cross check 0 times x1 plus 2 times x2 minus 2 times x3 plus x4 minus x5 is equal to minus 1. 3 times x1 minus x2 plus x3 minus 2 times x4 plus x5 is equal to 1. Last equation x1 plus 0 times x2 minus x3 plus x4 minus x5 is equal to 2. Now wait a minute. I stop recording, I cross check, and then I say if they are correct, you start solving. Okay, all these equations are correct. You do the, now I have shown you for 3 by 3. That means what is to be done is all these 1 1 2 2 3 3 4 4 5 5, these elements you are supposed to make them as pivot and they should be 1, and all the elements below that will be 0, and they have to be done very systematically. First column 0, then second column 0, then third column 0, fourth column 0. I mean below pivot you should go one by one, not simultaneously. And you can use 3 transformations: one flipping of rows, second multiplying a row by non-zero constant, and third adding another row with multiple of non-zero constant to the required. Okay, these are the 3 operations you can do. Get me the solution set of this. Okay, there is a correction in the first equation. Instead of plus x5, it is plus 3x5. x1 comes out to be, or let me write down it as matrix: x1, x2, x3, x4, x5 is equal to 1 minus 1 0 to 1. This is what eventually we'll get. And before this, if you really want to write down the corresponding last matrix equation, then it will be 1 1 1 1 1. Pivot elements 1, all 5, and everywhere else 0. This entire triangle is 0. This entire triangle is 0. That is how this matrix equation eventually will look like. Okay. Now, this system was designed to have a solution like this, and it is easy to design the system, but it is extremely difficult to decode it and get to the solution. Now, I won't ask you to do, I will do every time, but we need to learn some cases. Now, for example, 1, x plus y plus z is equal to 2, 2x minus y plus 2z is equal to minus 1, and x minus y plus z is equal to minus 3. So if this is a system of simultaneous equations, matrix equation 1 1 1 2, 2 minus 1 2 minus 1, 1 minus 1, 1 minus 3 augmented matrix. Now very quickly we will do this. 1, 1, 1, 2. If I want to make this 0, 0, that means I am subtracting 2 times 1 from 2. 2 times 1 from 2. Minus 3. 2 times 1. Subtract from again 0. 2 times 1, that is 4. Minus 5. And I can simultaneously do this 0 also, because this is now independent. So 0, so I am subtracting 1 from 3, minus 2, minus, this is 0. Is it correct? And then minus, this is subtracting, so minus 5. Am I making calculations correct or wrong? Minus 3, minus 2, 0, and this is 2 times this is subtracted from this, that is minus 2. 2 minus 2, minus 1 minus 2, 2 minus 2 minus 1 minus 4, which is correct. Now 1, this minus this is 0, this minus this is minus 2, this minus this is minus. Okay. Okay, this is the system. Now we were supposed to make this 1, and therefore we get 1, 1, 1, 2, 0, 1, 0, 5 by 3. Okay, and 0 minus 2, 0 minus 5. Then we are supposed to make this fellow 0. So 1, 1, 1, 2, 0, 1, 0, 5 by 3. If I want to make this is 0, what should I do? Multiply row number 2 and add. So 0, 0, 0, multiply row number 2 by 2 and add it to third. Is it correct? So 10 by 3 is to be added to minus 5. किती येणार उत्तर? 10 by 3 is to be added to minus 5. So 10 by 3 is to be added to minus 5, 15 by 3. So it is minus 5 by 3. बरोबर आहे करेक्ट. Is it correct? Because I have got something different written in my notebook, therefore I am just checking. Is this correct? So first and second row is same. Third row I am doing this fellow equal to 0. So R3 plus 2 times R2, R3 plus 2 times R2, R3 plus 2 times R2, which is minus 5 by minus 5 by 3. Is this correct? So this is the augmented matrix that we have. What can you conclude out of this? Now you wanted to make this one, but you can never make this one. Okay, so if we convert these equations now, x plus y plus z is equal to 2, y is equal to 5 by 3, and I mean 0x plus 0y plus y plus 0z is equal to 5 by 3. 0x plus 0y plus 0z is equal to minus 5 by 3. What can you conclude out of this? What will be the solution set of this system? 0, 0, 0 minus 5 by 3. So no solution. Why? Because no value of x comma y comma z will satisfy the last equation. No value of x comma y comma z will satisfy the last equation, and moreover you will find. Now how do we recognize this without reducing? Without reducing means whatever you have learned to do here, whatever we have learned to do here, upper triangular, lower triangular, the final version that you get is called row reduced echelon matrix. Those upper triangular, lower triangular, to make them scalar, diagonal, everything is 0 except diagonal. It is called row reduced echelon matrix, the final version. So when we try to convert the system into row reduced echelon matrix, we get a situation where the last row is 0, 0, 0 and k, where k is not equal to 0. And this is a into x is equal to b, where a is 0 but b is not equal to 0. I mean, that is what is the situation we are discussing. Now what do we mean by a 0? Now is determinant of a is 0. Okay, that is what is a mean. A is, in our system, ax is equal to b. If a is equal to 0 and b is not equal to 0, no solution. Correct? Exactly same situation here. Ax is equal to b, but a itself, this is a good looking matrix A. It is, I mean, we don't, it is not zero matrix, it is good looking matrix A. However, if you try to find out the determinant of that matrix, it is going to be 0. Now we know how to find out determinant of 3 by 3 matrix. Let us cross check whether it is 0. 1, 1, 1, 2 minus 1, 2, 1 minus 1, 1. Correct? Oh, now I have found out the mistake. Okay. So what is the determinant? 1 into minus 1 plus 2 is 1. Minus 1 into 2 minus 2, 0. Plus 1 into minus 2 plus 1. So 1, 0, minus 1, 0. So the determinant of this is 0, and see, we have calculated determinant of original matrix, but we said the system is equivalent, therefore we should have calculated determinant of 1, 1, 1, 0, 1, 0 and 0, 0, 0. If one row of the determinant is 0, 0, 0, of course the determinant is going to be 0. Because if you expand using the last row, of course every multiplication is going to be 0, and that is what is happening here. The last row is 0, 0, 0 and non-zero. However, if we could adjust some numbers, I think we should make this as minus 2, which means this is 2. Okay, and then you are making 2 minus, this is done, this is this minus this, so minus 1 minus 2, this is minus 3, it will become minus 3 here, minus 5 is correct. Then what you are trying to make is 1, so this will continue to remain minus 3 is equal to 3 minus 3, and then if this is minus 3, then you will end up getting this as 0, 0 and this also 0. Please cross check what I am trying to tell you now. If this coefficient is minus 2 here, Then what will happen is minus 2 will come here, minus 3 here, minus 3, and this will become 0, this will become 0, and this also will become 0, because we are subtracting minus, we are adding 15 by 3 minus 5 is 0. Do you understand? And therefore, if you write down the simultaneous equations for this matrix in red, you will get this fellow 0. Right? And now there is a question. If it was k, there is no solution. But suddenly, the moment you end up getting that entry 0, you have infinitely many solutions. You have infinitely many solutions here, because the last equation allows you to take any value of x, any value of y, any value of z, which will become 0. And now you have already fixed value of y is equal to pi by 3. Okay, and therefore, see, for any value of z, you will be able to find out the value of x, because y value is pi by 3. Any value of z you take, it will not impact the second equation because it is 0 z. So you take any value of z. So final solution set for this system of equation, which is x plus y plus z is equal to 2, 2x minus y plus 2z is equal to minus 1, and x minus 2y plus z is equal to minus 3. For this system, you can take any z. Your y value is 5 by 3. So can you tell me what value of x in terms of z? This is what is our solution set. You can take z is equal to z. That means any value of z which is a real number. Your y value is 5 by 3. Can you tell me x value? Yes, x is equal to 2 minus y minus z, and 2 minus 5 by 3 minus z, which is 1 by 3 minus z. X value will be 1 by 3 minus z, y value will be 5 by 3, and z value any z value. That means it has got infinitely many solutions, but it is not the entire domain. See, understand this. Domain is three-dimensional. However, your solution set is one-dimensional. You can take any value of z, and corresponding y and x values are fixed. So, solution set has infinitely many points, but the dimension of solution set is 1. And that we can find out in this matrix itself. Okay. Now I will erase this 5 by 3 and make it 0. This is 0. So here I got one pivot element. I have got another pivot element, but I failed to get the third pivot element. However, third equation is 0x plus 0y plus 0z is equal to 0. Hence, it has got infinitely many solutions. But because I failed to get the third pivot, this variable that I have is free variable. So how many free variables do I have now? It was a system of 3 by 3, out of which I could generate 2 pivots. Therefore, there is one free variable. And in terms of one free variable, I can report the solution set. My solution set will look like the matrix that I have written here. X, Y, Z will look like 1 by 3 minus Z, 5 by 3, Z. You let us put value of Z is equal to say 0. If we put value of Z is equal to 0, then the solution set will be say x1, y1, z1, or x0, y0, z0. By putting the value of 0, z0 is equal to 0, 0, 5 by 3, 1 by 3. Is it a solution set of this equation? 1 by 3 plus 5 by 3 plus 0 is equal to 2. True. 2 by 3 minus 5 by 3 plus 0 is equal to minus 1. True. 1 by 3 is 10 by 3 plus 0 is equal to minus 3. True. If you take value of z is equal to 1, then our solution set x1, y1, z1 solution set will be equal to 1, 5 by 3, 1 by 3 minus 1, that is minus 2 by 3. Let us cross check. Minus 2 by 3 plus 5 by 3 plus 1, is that equal to 2? Yes. Minus 4 by 3 minus 5 by 3 plus 2, is that equal to minus 1? Is that equal to minus 1? This is minus 9 by 3 minus 9 by 3 is minus 3 plus 2, yes, and third is also yes. So you take any value of z. Now yet another flexibility is there here, because x, y, z is our order of x, y, z, and the last equation became 0. Therefore, we are saying that z is our free variable. However, z need not be our free variable. You can have x also as your free variable, provided you should have started with z, y, x. The last variable is x, and you will get x as a variable. So, out of three variables that you have, x, y, z, only one variable you can have free. Remaining two are fixed, out of which in this particular problem y is also fixed, y is constant. Okay, so you can express x in terms of z or z in terms of x, doesn't matter. Here we have tried to express x in terms of z, but if I want to express z in terms of x, then it will be z is equal to 1 by 3 minus x. What is that? So you can have variable as x. Okay, now let me give you one more system which I will solve and show you the interpretation. Now, maybe you also can solve it. System of equation is x plus 2y plus z plus w is equal to 5. 2x minus y minus 2z plus w is equal to 0. 3x plus y minus z plus 2w is equal to 5, and x minus 3y minus 3z plus 0w is equal to minus 5. Maybe this is much easier compared to 5 by 5 which I have given you. Just get me the row reduced echelon matrix, upper triangular matrix. 1, 2, 1, 1, 5. 2 minus 1 minus 2, 1, 0. 3, 1 minus 1, 2, 5. 1 minus 3 minus 3, 0, minus 2. A lot of work. Let us see. 1, 2, 1, 1, 5, 0. 2 minus 3, 9. 2 times first row, minus 1 minus 4 minus 5 minus 4, 9 minus 3. This minus 2 minus 1, this minus 4 times that minus 10. 0, 3 times minus 6 minus 5. 3 now 2, 3, 1. 15 वजा 5 10. This minus this. 0, minus 1, minus 2, minus 1, 10, minus 10. 1, 2, 1, 1. Yes.
So that minus, it should be minus 4.
Here, minus 5.
Second row, third column.
2 times first row to be subtracted. This should be minus 4. बाकी बरोबर आहे. 3 times 3 minus 6 वजा minus 5 3 वजा minus. इथे पण चुकलं वाटतं.
सर त्याच्या खालच्या रो मध्ये पण करेक्ट आहे.
इथे -4 पाहिजे.
हो सर, आणि त्याच्या साईडला -1 पाहिजे.
-1 पाहिजे आणि हा
-10 पाहिजे.
-10. शेवटच्या रो मध्ये दिस बरोबर आहे कारण सिंपल सबट्रॅक्शन आहे. आता बरोबर आहे का? ओके. सो नाव लेट मी मेक इट 1 हियर, 0, 1, -4/5, -1/5, 2. Okay, then let me write it -1. Can you see the two rows are same? -4, -1, -10, 0, -1, -2, -1, -10. Okay, then we want to make this 0. So if I want to make this 0, 1, 2, 1, 1, 5, 0, 1, -4/5, -1/5, 2. If I want to make this 0, multiply this by 5 and add 0, 0.
So in the last row, it should be minus.
Here it should be plus. In the last row, is there any mistake?
In the second step.
In the second step, I am doing first, third minus first 0, third minus first is -5, third minus first
Yes, sir.
-4, third minus first is
Minus. So
third
that
minus.
is right.
Now correct, all 3 rows are same. So what will happen is, the moment you have 1 here, you have 0, 0, 0, and fourth row is also 0, 0. Okay, this is your final upper triangular. If calculations are correct, then this is your upper triangular matrix. You wanted to make 4 pivots, but you eventually got only 2. Okay, and therefore what is this equation that you have now? It is y minus 4/5z minus w/5 is equal to 2. Correct? Now here you cannot make pivot, however LHS is equal to 0 and RHS is also 0, 0. Therefore any value of z and any value of w is okay, and therefore y will be 4/5z plus w/5. 4/5z plus w/5 plus 2. Okay, and your x will be equal to 5 minus 2y minus z minus w, out of which you can put y there. 5 minus 2 inside bracket 4/5z plus w/5 plus 2 minus z minus w, and therefore you can express x also as constant, some k plus u times z plus w times 9 plus t times w. X and y are dependent on w and z. So your solution set will be x, y, z, w is equal to, you can quickly find out this. I mean, we need not be so lazy. Let me do it for you. Is equal to, constant term is minus 4 plus 5 is 1. Z is plus z. Coefficient of z is minus 8 by 5 minus 1. Minus 8 by 5 minus 1. And coefficient of w is minus 2 by 5 minus 1. That makes it 1 minus 8 and 5 13 by 5z minus 7 by 5 w. Okay, so x is equal to 1 minus 13 by 5z minus 7 by 5w. Y is equal to 2 plus 4 by 5z plus w by 5. Z is equal to z, w is equal to w. This is the solution set. Now this solution set can also be written as 1, 2, 0, 0 times constant plus z times minus 13 by 5 plus 4 by 5 0, 0 plus w times minus 7 by 5 1 by 5 0, 0. Zero, zero. So here it should be 1. That is z is equal to z we should get. And here it should be 1. Ray, check whether you are understanding what I am trying to do. I am doing it for numericals, but eventually we can something like this solution set for variables in general, for parameters. This is 5 by 5. Now, what is so good about this? Why is this happening? Is because the system of simultaneous equations, which if you observe that this is the row which is independent, this is the row which is independent. This row is achieved by adding R1 plus R2. Is this third row, and R2 minus R1 is this row. So for all practical purposes, this and this are only two linearly independent rows. These are dependent on them. So here the solution set has how many dimensions? You can choose Z, you can choose W. Therefore, system Rn was 4. N is equal to 4. N is equal to 4. How many pivots? 2. So, number of free variables equal to 4 minus 2 equal to 2. So, you can, out of 4 variables that you have, you can have 2 variables as free variables. Therefore, geometrically, number of variables, free variables 2, therefore geometrically, this is 2-dimensional solution set, which is a plane. Now, 4-dimensional system we cannot draw, but suppose it is a 4-dimensional system, the two-dimensional system which is plane is going to be the solution set of this system. Now 4 by 4 is beyond our imagination, but by using these calculations we can really understand what the system is. System is of 4 variables, out of which 2 variables are free and 2 are fixed. Therefore the eventual solution set that we get is two-dimensional, which is plane. In the earlier example, only one free variable, therefore the solution set we got was one-dimensional. That means it was a straight line, which was the solution set. Any point on that straight line would satisfy the given system of equations. Here, any point on this plane will satisfy the given system of solutions. And hence, now the number of pivots that you make are important. If this system was such that you ended non-zero constant here, say 1 after reduction, then the system will not have any solution. No value of x, y, z, w would satisfy the given solution set, given system of equation, because 0x plus 0y plus 0z plus 0w, we want to make it 1, which is impossible. So that is the empty set situation. What I am explaining you now is more than one solutions way of, if you end up getting all pivots, it's a unique solution, a particular solution. I mean, all those 4 hyperplanes that you have, they pass through a common point. If your pivot is completely satisfied, all n is equal to 4 and you end up getting 4 pivots, that means system does not have any free variable. It's a unique solution which satisfies the given system of simultaneous equations. Okay. So interpretation of row reduced matrix, that is what we have learned right now. I wait for some time. Okay. Now without numbers, let me give you in general, and I want you to write down the solutions. Matrix, there are 7 variables and 5 rows. Upper triangular, already row reduced echelon matrix. Now only some numericals are there, minus a1, minus a2, minus a3, minus a4, minus b1, minus b2. Okay, there are 7 variables, x1 to x7, and RHS we have 5 by 1 matrix, b1, b2, b3, 0, 0. Last 2 rows, if you see, everything is 0. Therefore, it has got infinitely many solutions. Correct. So, can you express this? Can you express this as, now I want you to write down x1, x2, x3, x4, x5, x6 and x7. That is what is the solution set. So x1 is equal to what? x2 is equal to, in this form, some constant vector multiplied by some free variable times second something plus the way I had written the earlier. Can we complete this exercise? Okay, change the constants in second row because I have used b1, b2, b3 in RHS. So these are c1 and c2. x7 is equal to b3. Second equation, x5 is equal to b2 minus b2 plus c1 x6 plus c2 x7, correct, which is b2 plus c1 x6 plus b3 c2. x5 is over. Now x3 is equal to b1 plus a1 x4 plus a2 x5 plus a3 x6 plus a4 x7, out of which x7 already I have, and x7 in terms of, okay, so what all I can substitute in case of x3 b1 plus a1 x4. x4 is going to be my free variable, plus x5 is dependent, a2 times b2 plus b3 c2 plus c1 x6, that is x5. x6 is my free variable, so a3 into x6 plus a4 b3. So what all constant terms are there? b1 plus a2 b2 plus a2 b3 c2 plus a4 b3, these are constant terms, plus a1 x4 plus a2 c1 x6, a2 c1 plus a3 x6. Okay, so I have expressed x3 in terms of x6, x4. Now that is all about it, and I have x2 as free variable, x1 as free variable, x7 is fixed. So maybe we can write down now the expression. This way we will write it later. We will first write down the expression. x1 is equal to x1 free, x2 is equal to x2 free, x3 is equal to, let us call this bracket as k1 constant plus a1 x4 plus k2 x6. Okay, so k1 plus a1 x4 plus k2 x6, that is x3. x4 is free. x5 we have got, let us call this as k3 plus c1 x6, that is x5. x6 is free variable and x7 is equal to b3, right? So this is what is your matrix, actually solutions. But if we want to write it as a multiplication, what all constants that we have? In fact, you have to write down all these equations in terms of constant plus something times x4. कसं करणार आहे बघूया जरा. आपल्याकडे व्हेरिएबल्स किती आहेत? दिस इज कॉन्स्टंट प्लस फ्री व्हेरिएबल x1 times, let me write it properly. I will fall short of time, but then we will complete it and end the meeting. x1, x2, x3, so this is equal to constant. So in the first equation there is no constant, 0, 0, k1 constant in the there, 0, third k3, 0, b3. These are the entries for constant, plus multiplier of x1 in In the first equation, you have 1 times x1 and there is no x1. 3, 4, 5, 6, 7. Okay. In the second equation, I mean for x2 multiplier, we don't have in the first equation, second equation 1, and we don't have anything. 4, 5, 6, 7 plus x3 times, now x3 is dependent, so it is not free, so it will not. x4 first case 0, second case 0, third we have x4 which is a1, fourth we have x4 1, 0, 0, 0. We don't have x4. I hope you are understanding. x5 is not free, so it is dependent. x6 0, we don't have 0. Third equation we have k2, fourth equation we have 0, fifth equation we have c1, then 1, 0. We had 4 independent variables and 3 dependent, so this is what is your solution set: x1, x2, x3, x4, x5, x6, x7. Okay, this is the way of writing. Actually, x1 is equal to 0 plus 1 x1 plus 0 x2 plus 0 x4 plus 0 x6. x2 is equal to 0 plus 0 x1 plus 1 x2 plus 0 x2 plus 0 x6. x3 is equal to k1 plus 0 x1 plus 0 x2 plus a1 x4 plus k2 x6. It is as simple as that. I hope you have understood. Let me stop at this point. You copy it, I will wait for some time. Otherwise, our lecture is over.